like to correct an error that I crept into the formula for the departure function in the TP domain for the entropy, and I point out where the source of the error is. That's an important point. We pointed out that for any property, the departure function given the temperature and pressure as a specification, that is, the state is has a temperature T1 and a pressure T1. So the ideal gas will also have the same temperature and pressure. We derived one formula which was 0 to T1, right? du by dp T1 minus du ig by dp also expresses the function of pressure. That difference being integrated with respect to pressure from the zero, which is the ideal gas range limit, to the actual pressure at which I want the departure function, and T1 appears as a parameter in the integral. So there is nothing wrong with this. And then I said to actually solve this, right, to actually compute this realistically, because the pressure is given usually as a function of volume and temperature. So the integral over P becomes inconvenient to handle. We have to convert it. So I said this is accomplished by a transformation P equal to P as a function. That is the actual equation of state is used as a transformation. Right? This is the actual equation of state of the substance, not the ideal gas. And then I wrote this as infinity to V1 expressed now as a function of V will then yield, and then on top of it I have the derivative of P with respect to V. It appears to be quite innocent and an easy, obvious consequence of this, because if I substitute for pressure as a function of volume and temperature, then this whole function would become a function of volume and the temperature which is evaluated at T1, the same thing. There is nothing wrong with this as such, but it can clearly, my idea was to give you a formula that you can use directly, and in trying to do that, I myself was led into an error. The error was, let us now take the example of, for H it doesn't matter because this term is 0, right? But for S, we know that ds by dp for any general substance, right, is given by minus dp by dt from one of the Maxwell's relation, and that further becomes dp by dt divided by dp by, there's also no problem here. Now, for the ideal gas, this is equal to minus R over P. That is also correct. So there is no error until then. But also the error came when I actually saw this, right, for S. And then I said you have to express in terms of V and T1, right? And then I immediately wrote this to be equal to minus V over T1. This is also correct in, if you look at it isolated, just focus on the ideal gas, right? That's also correct, because for the ideal gas, R over P is, PV is RT, so R over P would be V over T, and the T here is temperature. However, what I have done here is I have used PIG of VT1, but whereas my original, this is where the error is. Because what I have done, this is a mathematical transformation. Once I have this integral, this transformation applies for the entire integral. Because I cannot do the integration piece by piece. If you look at this, for instance, for S, this is now in itself. So I cannot handle that integral separately. But it can be easily shown the integral as a whole, right, is finite. Typically it will turn out to be a finite quantity, the integral as a whole. That's because you will find that this will also, because as p goes to 0 is when it blows up. But as p goes to 0, this will also tend towards the ideal gas limit, and so you will get a cancellation, right? And it will make sure that the whole integral doesn't blow up, right? So that's why it's important to keep the terms together. So the p equal to p of t1 applies to all the terms, both this and this, even though this corresponds to the ideal gas, right? So, but what I inadvertently did was applied the Pig for this term, which is not consistent with what I wanted to do. So let me write this first in terms of u equal to s. So it's important to be careful. There's nothing wrong with this, but you should remember where this came from. So this came from this, right? So what I did was I applied this transformation to this term, but I applied the ideal gas pressure equation to this term, which is not what should be done, right? So I will redo this and you will see where the difference is. Now, for u equal to s, ds by dp is obviously first minus dp by dt, expressed as a function of p1, and then this would be r over p minus r over p, so there is a minus sign. So I get plus r over p dp. So now I see that I want everything to be expressed in terms of v and t. So the whole integral has to be transformed to v as a function, p as a function of v and t. That's the transformation I will apply. Right? So the integral itself is going to transform all the terms within the integrand. Right? So now, obvious thing to do is now express this in terms of v and t1. So I'll get, first the limits have to change. I'll come to that shortly. So this will become dp by dt dt1 divided by dp by dt dt1. Right? And now this will remain plus r over. This is where the important is. What I did was I replaced this by p ideal gas, and then this is possible, but that's not what I wanted, because the transformation p equal to p of p even applies to all the terms in the integrand. So this is what it is, and then I have the term coming because of the transformation, the derivative of p with respect to v, that is the when I have, for example, integral a to b f of x dx, and I transform this using x equal to a function of u, then I get f of x of u, right? This is u of a and u of b, and I get dx by du du. So that is the additional term that I have to add. You might recall that if it is a double integral in the two variable domain, then it has to be replaced with a Jacobian of the transformation. But we don't need to deal with that complication here, because it's a pure single variable transformation. So the temperature is fixed, right? So this is what I have to deal with, right? And not this replaced by minus v over t1. So that's where the error is an important point, and you have to understand why, that has to be corrected, why that is not correct. Right? So I have to now handle this, and of course the limits of integration would be infinity v1. Again, let me make it very clear, the v1 actually corresponds to the volume of the actual state of the substance. This is the volume of the actual substance, specific volume, at the state T1 and T1. Okay? At the state specified by T1 and T1. Now this is the correct formula. I have to develop this further. So this would be infinity to d1. I will do it term by term. So I get dt by dt. Then I have this term. It is r over p dv by dv. So I can write this as r d logarithm of p over dv. Right? 1 over p dv by dv is p logarithm. dv. I can leave it like this. At least an integral of why I need to write that. Actually, you will see that why I can leave it as it is. In fact, I don't even have to use the logarithm. This will be 1 over p bar. I can leave it as it is because what I want finally to know is that given an equation of state, can I evaluate this departure function? Actually, if you erase out or strike out all that we wrote yesterday, so now this is the correct formula. I can, given an equation of state, I can calculate dp by dt, and I have to calculate the integral. This might actually go up, I might have to actually do it together, right? So I can write it together, infinity to d1, dv by dt, dg1 plus r over now I see why I went to the logarithm aspect shortly. I can leave it as it is. I can leave it as it is. Yeah, that is will come. Yeah, that is going to come. Yeah, that is here. This is in this term it cancels. In this term it will be there. There is a term in the denominator. So the first term, there are two terms. dv by dt minus dv by dt is replaced by this. R over p remains as it is, but now the measured as a function of p and d1. Right? That's the important change. Right? And then I have dp by dt multiplying the whole. So now if you look at it term by term, this is dp by dt by dp by dt, that will cancel. That's what I have written here. Then I have r over p expressed as a function of p and evaluated at d1 times dp by dt. That is going to be there for the second term. I cannot cancel it. This is what it is. Now let us look at what the departure function is in the TV domain. That is when D1 and B1 are specified. Right? So now let's look at that. Is equal to integral infinity to B1 ds by dv now. Here there is no problem with transforming and so on. This is actually going to be, you will see, very easy to write down. Nothing much to do. Because I know one of the maximum relation ds by dv is dv by dt. Right? So that I can write as infinity to d1 dt. And dp by dt for the ideal gas, all I have to do is once I put in the general formula, just calculate it for the ideal gas directly, because we know p is equal to RT by b. dp by dt is R over b. So very simple. dv. Now the question I raised in the previous class, are these two equal? Certainly one of the terms I have recovered. What about this? This now has a form quite different from this. So if I want to prove conclusively whether they are equal or not, I have to establish a connection between this term and this term. So that I need to further work on it. So I write that term alone as integral R over E bar dt by dt as integral. That's why I have to, otherwise I can leave it as it is. Right? Because I have given an equation state, I can calculate 1 over p dp by dv. expressed as a function of b and d1, I have to integrate it. Whether it would be possible analytically to do it or I have to do it numerically depends on the particular equation of state that is given. Right? But now if I want to establish a connection between these two, certainly I have to work further on that and see whether in fact a connection can be established. Now you see, if you proceed this way, this can now be written as R, the logarithm of the pressure, which is again a function of B and D1. Now I will write this as that is a trick, because I want R over B, right? So what I will write this as D logarithm of dB by dB. So I'm taking the product. Now D logarithm dB is simply d by dB. Logarithm of dB is logarithm of t plus logarithm of d. So I have the derivative d by dB of logarithm of t1t, but now I am including the term logarithm of t plus logarithm of v, right? And so I have to subtract what I have added, because I want only this. I have only this. So I am adding this, so I have to subtract. This is why we write it like this. So I have to subtract d logarithm of v by dv. So I can write this as d logarithm of dv by dv minus d logarithm of v differentiated with respect to v. So I am simply adding and subtracting two equal terms. One of the terms I am joining it with d logarithm of v by dv and writing it as d logarithm of dv by dv. Now I know the d logarithm of v by dv is simply, it's actually the full derivative, it's simply 1 over v, and so I get R integral infinity to v1 d logarithm of dv by dv minus integral R infinity over v1 dv by v. So I have got this here, so I can now write that I will combine those two terms. I can write this as integral infinity to, that is the departure function at a fixed t and p, right, can be written as, I now bring the minus r over v into this, because that's what I have here. But then that's not all. I'm having now an extra term which is infinity to v1 d logarithm of dv by dv. So this is of the form integral a to b f prime of x dx. This is actually the derivative of the logarithm of p. F is here logarithm of pv, right? Which is a function of b, and of course the d1 as a parameter, right? So that clearly is f of b minus f of a, right? Because the derivative of some quantity with respect to b. You have to keep that in mind. So f here is logarithm of pv, right? And that is integrated with respect to b. When you integrate the derivative of a function, you recover the function. There's a famous theorem of calculus, fundamental theorem of calculus, right? The integral of the derivative is a function itself, but now it's a definite integral between two limits, so I have to calculate the function between the two limits. So clearly, this is plus r logarithm, right, of pv evaluated between the two limits infinity and v1. So this is the ideal gas limit, and this is the actual substance d1, d1, d1. That's what you have to. So now I have got p also. In fact, I can write this as p of d1. evaluated at the two limits, right? So clearly this is this plus R logarithm. The top P of P1 is simply P1. So P1, P1, and then minus the logarithm of PV in the ideal gas limit will be RT1. So I am getting this. Right? So this is the extra term, and so I can now write S minus SIG of P1 is equal to S minus SIG. Really it is not equal. The two are not equal. Right? In fact, it is equal to S minus SIG P1 plus R logarithm of P1 by RT1. So the two are not equal, right? And the difference is given by R logarithm of P1 by RT1. So now the question is why? Well, for H minus HIG, the T1 H minus HIG TV T1 was equal to H minus HIG T1. While for the entropy, the two are not equal. The two departure functions are not equal. This is important to keep in mind because we said that it's easier to work in the TP domain. So you can ask, why do we need the TP departure functions at all? You will see the relevance of the TP departure function. First of all, I can work in the TP domain, but I will get only the departure function in the for TP directly. So that's very easy. Okay? You can see how easily this was obtained and how difficult it was to get all of this, do the transformation and get it, to get S minus. So the two are equal, then there is no need to consider the TP at all. I can directly work in the TP and get that departure function and say that it's equal to the TP departure function. So that was the same quantity S minus SIG. Right? How should it matter whether I am specifying the temperature and pressure or the temperature and volume? Right? So why is it different for S but not for H? That's the question. Right? So the point, I will make the question more specific. Now if you see here, compare this and this, right? This has S T1. This has S T1. So this has SIG T1. This is SIG T1. So the difference of two terms, right? Now the question is S of T1 equal to or not equal to? Not equal. Let me complete the question. Right? SIG of T1 is it equal to or not equal to? So there is a difference in two terms. The two terms are different, but each term is a difference of two terms. So the two terms not to be different. Either both the terms S may be different, SIG may be also different, or one of them could be equal to the other, corresponding other quantity, and the other term could be different. So there are various possibilities. So the question is, let's first answer this first question. Is SF evaluated at T1 equal to S evaluated at T1 or not? Not equal. How many of you think that it is equal? Nobody thinks it's equal. The two are equal, or all of you think it's not equal? Not equal. Is there anyone willing to claim, at least for the sake of claiming? Because there are some people, who say something just because the majority are saying something. So is there anyone who wants to claim?
So we cannot actually say that the difference frequency is not equal.
No, I am now asking the question. I am now trying to find the root of the difference. Right? So now directly forget about the differences. Just look at this. Given, of course, that we have seen that T1 is given that you should know what T1 means. So the question is, given you should know what the meaning of P1, V1 and T1 are. T1 is specified. V1 is the volume corresponding to that state. So the question is this equal or not equal? So the answer predominantly seems to be not equal, right? Nobody seems to be willing to say that they are actually equal. Let's now come to the second point. Is the ideal gas T1 is it equal to or not equal to the ideal gas entropy at T1 V1? Equal. So you are saying that because this is not equal, this difference is not equal, right? Your answer is wrong on both counts. Because this is actually equal and this is not equal. I will now explain. Really, you are not even. This has actually to do with the error that I made yesterday. It's related to that, right? Somewhat related. So it's an important point, and you should understand why the entropy of the actual substance is the same, and the entropy of the ideal gas corresponding to that substance seems to depend on whether you specify T1 V1 or T1 V1. So let's now look at this. So suppose let's consider T1 V1 as the specification. I have to start somewhere. I can either start from given T1 V1, right? Or I can start from T1 V1. I have to start somewhere. You can phrase the argument in either way. So I will take that T1 V1 are given. Right? So I am saying that I am interested in the departure function of a particular state of a substance or a particular property, right? Whose temperature is T1 and whose pressure is P1. Now I ask two questions. The specific volume corresponding to this actual substance, the ideal gas of that substance, given T1 and P1, what would be the specific volume of the actual substance? Right? The answer is here. Whatever quantity satisfies that equation, we have taken that it is V1 that satisfies that equation. So clearly it is V1. What about the specific volume of the ideal gas corresponding to that substance? RT1 by P1, right? So that is where the difference is. So either I choose T1 V1 or T1 V1, it doesn't matter for the actual substance because they both correspond to the same state. Now the state is 1, I am calling it state 1. I can either, so what are the properties of the state of the actual substance? Its temperature is T1, so the actual substance its temperature is T1, pressure is P1, the volume is V1. So I can specify any two of the quantities for this actual substance to determine its entropy, right? So I will now distinguish between two different representations of the same quantity, which is, let's say S equal to S cap of PE and S equal to S bar of VE. So we have already seen the same quantity can be either expressed in terms of volume and temperature or pressure and temperature or even pressure and volume if you wish. But here the question is between volume and temperature on the one hand, the pressure and temperature on the other, right? So the same quantity can be expressed in terms of different sets of variables. We have seen it again and again and again. This is what you have to understand in thermodynamics. This is what complicates the matter, right? So now, if for the actual substance, I am given T1 and P1. There are two options. One, I can use the cap function and calculate. So that would be S1. I'm focusing only on the actual substance. Right? I can calculate what the entropy is. Or if I am only given this, if I have only that, or if I want to, for some reason, just for the fun of it, I want to calculate the S using that S bar, which is given as a function of V and T, what do I need to know? But at T1, P1, that's the state is specified, there's no change from that. So if I want to use that bar function, what is it that I need to additionally find? What is the quantity I need to find? First tell me that, then you can tell me how you are going to find it. B, the volume corresponding to T1 and P1 is what I have to find. So I go and find that. P1 from P1 equal to, I have to solve for this and find the volume. The equation state of the actual substance. Right? So I find the volume, that is V1. So I can go and find S bar at T1 V1. Will this be equal to S1 or not? That is calculated from the function of temperature and pressure. Let's say that also is given. So I go and substitute T1 P1 in that, I get one value. Or roundabout way, I go and calculate the volume corresponding to that state and use the bar function. Is it going to be equal to S1 or not? Yes or no? It is going to be, because it's the same state, right? So all the three quantities T1, P1 and V1 correspond to the same state. So whether I use the cap function, which is a function of P and T, or the bar function, which is a function of P and T, it should not matter. Provided those transformations are, the functions are correct functions. Right? So it should not matter. On the other hand, right, so I will put this in brackets. Let's take the ideal gas. So for the ideal gas also, I can look at the ideal gas entropy also either in terms of temperature and pressure or in terms of temperature and volume. That function will obviously differ from the function for the corresponding function for the actual substance, right? So I can do that. So now let us say that T1, P1 is specified, right? So there are two options again, right? So I can calculate SIG, right? One, but now if I want to use the bar function, right? S bar, even is the same. What is the volume I would use? RT1 by, not V1, but actually RT1 by V1. Right? So that is where the difference is. Now I can easily establish this difference based on those ideas. So I have now convinced you, hopefully, that the difference, right, from this, let's now calculate the difference independently. I have already calculated separately S minus Sij at T1 P1 and S minus Sij T1 P1, right? And I found the difference. Now I will approach it in a different way. I just focus on the difference, having established that S at P1 T1 is the same as S at T1 P1. If you are not convinced of that, then I cannot help you at this stage, right? So for those of you who are convinced of that, now I will calculate the difference in a different way. that will make the argument clear. So I am calculating S minus SIT evaluated at T1, P1 minus S minus SIT evaluated at T1, V1. Right? So I will cancel this. I can write as S evaluated at T1, P1. I am deliberately not writing it as a function. Right? S corresponding to the specification T1 and P1 minus S of the actual substance corresponding to T1 and P1. Very importantly, P1 is given by this. That is very important. Not just any volume. It's a volume corresponding to the state specified by P1, T1. Right? That's very important. Then minus, I have SIT of T1, P1 minus SIT of T1, P1. So this is 0. I have established that because both those entropies correspond to the same state of the actual substance. Right? So they have 0. Now what about this difference? So to bring one is evaluated at T and P or the specification, another is T and P. Right? So if I want to bring the two together under one framework, either I express both of them as functions of T and P, or I express both of them as functions of T and P. I can choose either one of them. It depends on which you want to express. So let's say the first is readily available. So I can say that this is S bar IG T1 V1. Because T1 V1 are given to me as the temperature and volume of the ideal gas corresponding to that substance. So I go directly to the bar function and evaluate that entropy. Now minus SIG I'm sorry, plus, this is plus, right? This is plus. So this is going to be the difference, right? So now I can, of course, you can say that well, T1 and P1 are given, so why do you need to go to the bar, right, function? I can write this as, you can write it, but however, if I want to calculate the difference, this is already expressed in terms of T1 and P1, so I also want to express this in terms of the bar function. T1 is the same, right? Now I want, okay, I'm looking at the converse of what I wrote, which is good. I have already pointed out how to handle it in one representation. This is another representation. So what would be the volume corresponding to T1, P1? The volume of the ideal gas now corresponding to T1 and P1. So R T1 by P1. Right? I don't know, maybe that's what I had there also. Okay. Yeah, that's exactly what I had there also. Right? So there also I expressed it in terms of bar, but you can also write this in terms of the cap and then this directly in terms of the cap. You can do that and verify whether the results are the same. So now, this is a difference in entropy of the ideal gas. The temperature between two states whose temperatures are the same but whose volumes are different. So if I want to write this as an integral, what integral would appear? What would be within the integral? ds by dv, right? Because it's a change only in volume. Temperature is the same, but it's corresponding to the ideal gas. So it's very important to keep explicit the variables. When you make the variables explicit, then you are also saying that I am adopting that function. Whether you call it bar or cap or don't call it anything at all. You make the variables explicit, then it's clear. So express the function of those two variables. dv, v, t1, dv. Now what would be the lower limit? RT1 by P1, because that is what is having a negative sign, and this is P1, that is the specific volume of the actual substance, right? So now what is dSig by dB? We already know what it is. It is dP by dt generally, but it is R by V for the ideal gas. So that's all I'm focusing on. So this would be integral R by V dV from RT1 by P1 to P1, and so this would be R logarithm of P1 V1 by RT1. So I've recovered that difference S minus SI T1 P1, that's what I had, right? Minus S minus SI T1 V1, here I have written it as equal, so I'll make it clear. Equal to R logarithm of P1 V1 by RT1. That is something that I established independently. By calculating the two independently, I established that. That is fine. That makes it clear once and for all that the two are different. But this gives a better motivation as what is the root of the difference. And you can now see why for adopting the same argument for H, why it didn't make any difference which domain we operate in, because clearly there the contribution will be dH by dV, which is zero of the ideal gas. So clearly you can now infer for the internal energy also the two departure functions will be the same. This now also gives you a way to evaluate the departure functions for the other quantities, namely A and G, which we haven't written down. So let me quickly write down those departure functions too, right, and then leave it for you to prove those. Then we'll continue from here. So I just want you to go through it your own way. Maybe you will consult some of the books how it has been done and check whether in fact these results are matching. But important is the explanation, that is more important. It gives you a feel for what is causing the problem, right? So when we say T1 V1 and T1 V1, as far as the actual substance is concerned, they correspond to the same state. But as far as the ideal gas is concerned, they correspond to two different states of the ideal gas, right? So you have to find, if you're stuck with T1 V1, you have to find the pressure corresponding to the ideal gas state. So that is the difference. So now I write the other. So H and S I have already written, but I will type it and give it to you separately in assignment sheet. But E, I'll just write down the formula. E minus EIT, both the departure functions are the same, is equal to, very easy to write down in fact, infinity to D1, T1 dP by dt of V T1 minus P dP. So you will see that this can be very easy. Now that you've got H and S, all the others can be simply got from definition, because we know that E is equal to H minus PB. So since I know this, I know what the departure for this is. So PB minus RT, so I can easily calculate that. Similarly, A is E minus PES. So when I know the departure function for E and for S, I can calculate it. And G is, either way I can do it, A plus PB or H minus ES. So you can write G minus IG as H, and so on, and you can get it, or you can get it directly also. I leave it as an exercise for you to directly approach these for E, G and A and see if you can get it. You will find some problem for A and G. You will find it easier to do it using these definitions. Now A minus AIG of T1 V1 is equal to integral infinity to V1 RT1 by D minus E of VT1 dV, and A minus AIG of T1. So you will now see that this, all of this again, but plus some additional terms would come in for T1 P1. So this is the same, and then we get minus the same term minus RT1, logarithm of T1 by RT1. Similarly, G minus KIG of T1 V1 is equal to infinity to V1 RT1 by V minus T of T1 dV. First we have addition terms here also, minus just as we had for the enthalpy. And now G minus TIG of T1 is all of this minus RT1 logarithm of T1 V1 by RT1. Some extra terms come in when you are looking at the departure function in the TP specification for both S, G and A. Whereas for E and H, the two are the same because neither the internal energy of the ideal gas nor the enthalpy of the ideal gas are dependent on volume or pressure. So it doesn't matter what the specification is, as long as the T, which is equal to T1 in both the specifications, is the same, those departure functions will be the same. So if I want to derive this, compare it with what is there in the books, and then if you have any questions on the derivation, right, we will take a look at it again in the next class. But I want to move on from here. The very important quantity is this, based on which we will define what is called as the fugacity, which is a very widely used quantity, right? So that is a very important departure function. We will focus on that in the next class. Are there any questions? We are out of time, so if there are any questions you can ask.